So today's announcements are, yes, the final is 7:30 a.m. I am so sorry, I did not pick that. It's Wednesday of finals week, and we have the room assigned as of last week. It's going to be in Math 100 where we have the exam review sessions. So if you don't know where that is, make sure you go check it out ahead of time. And then the exam review, I'm still trying to get the details nailed down, but I'm aiming for sometime on Sunday, 5/5, details to be determined. And then Sapling Chapter 23 I haven't opened yet, but I am going to open it today, and then it'll be due 9 a.m. Friday next week, because I'm going to finish it up Friday this week. Actually, probably going to finish this up Wednesday, so let's actually change this to, sorry, but it's next week at least, so you guys still have a while. But I guess having stuff due on dead day is kind of a no-no now that I think about it anyway, so yeah. And then FCQs are now open online, so you should have gotten an email with details about how to fill those in. I guess just kind of my usual spiel about those is, numerical ratings are sort of useful, but if you really have like any particular thing that worked well for you or didn't work well for you or that you liked or hated, like try to go into more detail if you can. Like I really do care about those and try to incorporate them in future years, which is why I have things like using the squeegee bucket and doing unlimited tries on sapling and all that stuff. So if you want to maybe help out future generations of people taking this class, let me know if stuff needs to change or is fine or what have you. Okay, so any questions about that?
So are we not going to have a sapling for chapter 4?
So I think the way I did it last semester is just set the due date right at the start of the final, which I'm going to have to get back to you on whether that's okay or not. I guess, yeah, no one's complained about it in the past semester, but that doesn't necessarily mean it's great. So yeah, I'll have to figure out if that's actually legit or not. But if not, then I guess I'll make it available and then figure out how to like curve everything else upwards for the rest of the homeworks. So. Okay. Actually, one other thing is someone requested that I make all the saplings available again for people to sort of practice on for the final. I think what I'm going to do is once the sapling chapter 23 due date passes, I'm going to export the grades for that and get everything in the grade book for all the chapters so far because a few people like got extended due dates and so a few things have changed. So I'm going to get all those posted to Canvas and then I'm just going to purge like all records of your previous attempts on sapling. It looks like there's no way to reopen it without just like clearing your progress so far.
You can actually go back and look at past sapling questions and
Okay.
scroll through your past attempts and stuff too.
Okay. I guess like when I looked at it with another student like earlier this semester, we weren't able to figure it out, but I may see if we can just do that so then you don't lose everything. But one way or another, I'm planning on sort of having it so it's available as a study tool for you guys. So, okay, questions about that? Okay, cool. So now back into material. Okay, so what we started looking at last time is amines and how to make sure that we only alkylate once. Okay, so we saw that if we try doing SN2 on an alkyl halide, which kind of sounds like the most immediately obvious way to do it, then we run into overalkylation where we may stick on multiple alkyl groups. Possibly limited by stoichiometry and sterics, but I wouldn't count on it. So we saw a couple methods that I'm not going to review too much, but reductive amination was one. That's basically make an imine, reduce it with something that looks kind of like sodium borohydride, only weaker. And then the other one we looked at was acylation, then reduction. So basically make an amide and then hit it with LAH. Okay. The third one that we're going to look at today is actually SN2. It's just significantly modified from just regular amine SN2. So this is called the Gabriel synthesis. Okay, so this is a great way to get just primary amines with a single R group on the end at the end. So it's not great for if you already have an R group on there. Okay, so what we're going to do is use this molecule. It's an aromatic ring. So if we had two OHs on here, this is not actually part of what we're doing, but it's sort of what this is named after. This is PHTH phthalic acid. It's where the PHTH group in phenolphthalein comes from, if you remember that indicator from Gen Chem. What we're actually going to use is this, but as sort of a weird double amide is how you can think of it. So both carboxylic acids, it turns out you can attach to the same nitrogen, this, and so this also has an H on it. And it turns out that H is, not too surprisingly, very ready to come off the molecule, because if we do that, it's sort of like when we're making an enolate in between two carbonyls, like we've got a minus charge on N, but we can use resonance to kick it out to here or out to here, and it's very well stabilized. So let's see. So what we're going to do is hit this with KOH, which turns out to be enough to deprotonate it. Okay. Okay. So this is something you can actually buy commercially. You don't actually have to make it yourself. But think of it as kind of like an enolate, but also kind of like an amide. This is called potassium phthalimide. And it turns out it's great at doing SN2 on an alkyl halide, but it's limited to doing it just once. So if we bring in some kind of alkyl halide, it'll do SN2 on there. Get a single copy of the R group. And you might be wondering how come the other lone pair doesn't go out and do that, like we saw that was a problem before. Turns out that the only reason this is only capable of, this is even capable of doing it the first time is just because of the negative charge. The remaining lone pair is so tied up in resonance to the carbonyls already that it's not actually reactive enough to do SN2 at any reasonable speed. So it pretty much does it once and then stops. And then what we can do is pretty much just a amide hydrolysis on this thing. So either acid and heat or base and heat in water. And that will get you the acid back. And it will also free up the amine. So I guess when we were looking at this from the carboxylic acid's point of view, this would be like our major product. We spit out whatever dicarboxylic acid in this case. But we're also spitting out a copy of the amine from the amide, and that's actually the major product that we care about making. Thank you. Okay. So when you're doing this in a synthesis, if you want to make just an amine with a single R group of your choice on it, provided, of course, that R is SN2 capable, I sort of left it really vague, but it's got to be, primary, secondary, then you can use the Gabriel synthesis and just buy potassium phthalimide and just go straight from there. Okay. So questions about that? So I guess how you could write this overall. Depending on whether you're looking at this from R's point of view, let's do that. So RBR, you would do, first of all, potassium phthalimide, and then hydrolysis, and that would get you a single primary amine there instead of the halide. Okay, so questions about that? Yeah?
When would you use acid versus base in that final step?
So I guess they're almost interchangeable. The only downside is if you do use acid, then you'll end up with the nitrogen in the wrong protonation step, or protonation state. And so I guess then in that case you'd have to do a quick base wash afterwards. And so probably if you want to keep it simpler, doing it as base is going to be easier. Yeah. In that case, you're also going to end up with the wrong protonation state on the carboxylic acid, but we don't really care. So,
So you said use base, we'll get the carboxylate version.
Yeah. Yeah, so one way or another, one of these is going to be having a charge on it. But I guess if you're doing an extraction afterwards to separate them out, that's making things easier for you, I guess. Yeah. Okay. Any other questions about this one? Yeah.
There's not anything else you could add to like sort of the base.
I mean, like, probably just acid to neutralize it out. But I guess, like, if we're doing base, then, you know, that's going to give us the right protonation state on the nitrogen anyway. So that works out. Okay. So that's it for Hofmann. That's kind of the third of the methods. I guess, like I said last time, if you know one of these options out of the three, reductive amination is probably the most useful one to know, because we're not limited by SN2 ability. We're not limited by what the exact nature of the R group is. And we can, you know, add R groups to a nitrogen that already has existing R groups. So for synthesis, most useful. Okay. Alrighty, so that's all three of those ones. So we've looked at how to stick nitrogen onto a molecule and make an amine. What we're going to look at briefly now is how to get nitrogen back off a molecule. So Hofmann elimination is what we're going to look at here. Okay. So we're going to bump into a lot of the same issues that we do with getting OH off of a molecule, where if you try to hit it with a base, it's just going to deprotonate the group and you're not going to get anywhere. So we're going to have to convert it to a good leaving group first if we want to do some kind of elimination. And traditionally, the way that we do that is actually by taking advantage of something that I mentioned last time, which is overalkylation. So we're just going to cram a whole bunch of methyl groups onto the nitrogen. So like say we're trying to get the amine off of this molecule and do some kind of elimination. What we're going to do first is just hit it with a whole bunch of methyl iodide, actually. And like we saw last time, that's going to end up with nitrogen getting as many alkyl groups as it can hold, to the point where it's actually got a positive charge. And I guess I didn't emphasize the counterion before, but that actually turns out to be somewhat important for this reaction. So right now what we have is an I- floating around nearby, which is a really weak base and is not going to do any sort of useful elimination. It's not like strong enough to do E2 or anything. Okay, so now what we're going to do is do a swap so that the iodine counterion is getting replaced with a much stronger base. And the way we do that is by throwing in something that really, really wants to bind to iodine, and we'll spit out a different counterion in exchange. And it turns out silver oxide. If you remember from Gen Chem, you may or may not have seen that silver iodide is this really insoluble precipitate. So like silver and iodine really like each other. If you throw this in with silver iodide, the silver and the iodine are just going to go off together. And you're going to end up with an OH minus as your counterion that's left behind. So silver iodide precipitates out. Okay, so this might look ridiculous, like why are we bothering about counterions when we haven't at any point during the past year pretty much? But this is the counterion that's actually the strong base that's going to do elimination. So strong base, good nucleophile. We would normally expect Zaitsev or anti-Zaitsev from that thing. Zaitsev, right? Yeah, because it's small and not sterically hindered. But this molecule is really sterically hindered. So it turns out even though this is actually small enough that it's going to prefer doing Zaitsev style elimination, more often than not, it's actually going to be forced, whether it likes it or not, to do anti-Zaitsev style elimination. So I sort of might have mentioned in OChem 1 that anti-Zaitsev, another name for that is Hofmann Elimination. That's actually where this reaction, or that's actually where this name comes from, is from this reaction. Like Hofmann started doing this and realized that it was actually favoring the less substituted alkene when this happened. So we're going to do an E2 style elimination favoring the anti-Zaitsev products. So anti-Zaitsev, aka Hofmann style. And we get the alkene at the less substituted position. Okay. So pretty much if we want to get a nitrogen off of our molecule, this is about the only good way to do it. Just alkylate, swap out the counterion, and then I think this goes more easily if you heat it up on the elimination stage. And then you end up with the anti-Zaitsev alkene. So if that wasn't the alkene that you wanted, then you can use sort of some old OChem 1 chemistry and move it around or do whatever to that alkene that you need. Okay, questions about that one? Okay, cool. Okay, so we've looked at adding nitrogen to alkyl groups. We've looked at removing it from alkyl groups. Now we're going to look at some aromatic stuff for pretty much the rest of this chapter, except for right at the end. Okay. So, one sort of field where nitrogen's been studied a lot is when it's attached to aromatic rings. So, we're going to go back and re-examine some of the EAS reactions a little bit, but specifically when they're on aniline or its derivatives. So there's aniline as a reminder. It's an aromatic ring with an NH2. And so you might remember that this, kind of like an OH group, it's an atom with a lone pair attached directly to the ring. So it's activating, strongly activating, and OP directing. So if we hit this with, say, halogenating conditions, and there's actually something weird about those that I'll mention in a second here. It's actually so strongly activating that it's very difficult to stop this reaction after just one addition. And so typically if you try doing a lot of reactions from the EAS kind of category on this molecule, it's going to just add to every possible ortho and para position, even if we don't even include the catalyst that we would typically have to use for this. So we're not even using FeBr3. It's just Br2 by itself, and it just sticks all over the ring. So even without FeBr3, nitrogen kind of gets a little bit carried away in this reaction as well. So, okay, so one thing that we can do to try getting around this is that lone pair is sort of responsible for this hugely activating effect. What if we try tying up the lone pair with something else? So if we take this and use conditions where the nitrogen might actually get protonated during an EAS reaction, so for example, HNO3 and H2SO4, we're going to get a mixture of some of this, like a little tiny amount of the unprotonated form, plus mostly the protonated form, NH3+. And because this has no lone pair and in fact has a full-on positive charge, this group is as opposed to the activating OP nature of the starting material, this one is strongly deactivating. And meta-directing. So this is mostly what we have in the mixture, but it's also much slower at doing the reaction than the activating group was originally. And so it turns out we're actually going to get pretty comparable amounts of product from the molecule being in this form versus from it being in this form, because there's less of this, but it's a lot faster. So we're going to get not too far off, like even amounts of the ortho and the meta and the para out of this, which is not something we've seen before. So this is not a great setup because we don't want to have 3 different things to deal with separating out from each other. Okay, questions about those? Okay. So what else can we do to tie up the lone pair in a way that won't just completely change the reactivity of that group? The answer is something that we've sort of done, I guess, a little bit in the past, and that is using resonance to tie up the lone pair instead. So resonance into a carbonyl. So what we're going to do is just stick an acyl group onto the nitrogen. So NH2 here. Easiest way to make an amide is from the acid chloride. And we're making an amide here. And now it still has a lone pair, so it's still ortho-para directing. But it's much less activating than it was before. Just because that lone pair is too busy to go into the ring and do resonance and donate electrons as much as it was before, because it's now tied up into resonance, both into the ring and into the carbonyl. Okay, so now this is going to react in a more reasonable way. And also the lone pair is much less likely to get protonated by acidic conditions because it's tied up in resonance. So we can actually get away with doing acidic reactions like nitration again. And get this. I'll just show the para, but ortho would be getting produced as well. So we get the product that we want without having to worry about the meta being formed. And now if we want, we can hydrolyze the carbonyl back off. Okay, so it's sort of like protecting group chemistry where we turn it into a slightly different functional group. We do the chemistry that we want to safely, and then we get it back off at the end. But I guess the protection is not quite so much for the nitrogen itself as it is for the ring that it's attached to, preventing that from doing anything weird. Okay, so I guess not really any new reactions here. It's just taking advantage of ones that we've already seen and putting them together in a way that gives us what we want at the end. So questions about that? Uh-huh.
So can we not use the top one there and say that we only get one of those products for like a synthesis?
Yeah, I guess like in the past we've been like, well, you get an ortho-para mixture, there's nothing to do about it, just keep the one that you want. But I don't know, I guess if you're only getting about a third of the yield that you want, that's not as good. Now that we have better workarounds like this, you'll still only get like half-ish of the stuff that you want, but yeah, if you can, like, try not to use this conditions, like, just because we can do better now, so, yeah. Okay, other questions about that? Yep.
So you'll be able to use ALCL3 purity instead, or else it has these other functional ring as well.
Yeah, probably. So, I mean, if that's what you're going for, but then, like, the question is, would the ALCL3 get there first and, like, just alkylate the ring in a bunch of places? So, yeah, better to do it stepwise, protect the nitrogen, then do whatever EAS, and then deprotect. Okay. All right, so that's sort of a combination of old stuff that we're seeing. The next one that we're going to look at is, again, aromatic rings, but in a new way that we haven't explicitly seen before. So now we're getting into diazonium chemistry. Okay, so we've actually seen a little bit of diazonium before. If you guys remember, like this thing was sort of a good way to make methyl esters pretty easily because the CH2 ripped off a proton and became methyl with, well here, let me actually draw that out. That can rip off a proton, become CH3, this N triple bond N on it, and then this can come in, do SN2, kick that out. Okay, and this whole thing is driven by nitrogen just wanting to go off triple bonded together. All right, so we saw that a few chapters back. What we're going to look at now is actually some new things that we can do with this diazonium group because this is nitrogen chemistry again. So we're going to look at how to make this and also some other really cool and useful stuff that we can do with it. So to actually make this from an amine, so this is called the diazo group. We're gonna start out by having whatever amine. I'm just gonna use the same one we used for eliminations there. and we're going to react it with sodium nitrite. Note that this is not NaNO3 like we're used to seeing HNO3. This is actually a different oxidation state on the nitrogen, so NaNO2. We're not going to go into the mechanism for that though, but I think there's one question near the end of the chapter that actually walks you through how to like figure out that mechanism for yourself if you're curious. And we're going to use acid and H2O. So basically, these are all there as a way of making HNO2 or nitrous acid. Which is what's actually going to do the conversion on the molecule. So very briefly what happens is this thing, you get N triple bond N with a positive charge there. If this were a methyl group or like a CH2 minus group, then it would be stable enough to sort of stand around like that for long enough that we could do some chemistry with it. Turns out with no negative charge on this molecule and also with like a molecule that can more steadily support a carbocation, that group is just going to immediately detach and go off on its own. So this whole thing is actually too unstable to isolate. Because you immediately get carbocation. And then from there, you're going to get a mixture of E1, so Zaitsev and anti-Zaitsev together. And also some SN1 from the water being around. Okay, so because it leaves a relatively stable carbocation after it drops off, it's just out of there immediately, and then the molecule just has to finish up the reaction however it can to get stable, so either by doing an elimination or an SN1. Okay, so long story short, alkyl diazoniums are pretty unstable and don't do anything super useful or new. Okay, so questions about that part? Okay, cool. So if we want to avoid this, let's try something where you can't really make a stable carbocation. So aromatic rings, like aryl carbocations, or aryl diazoniums, are a good way to do this. So if we try doing it up here, starting with aniline, and again, NaNO2, HCl, H2O. We're going to get this, and that nitrogen is not really going to go anywhere in a hurry just because there's no way it can drop off and leave a carbocation behind. It's still not super stable. But it's at least good enough to isolate. All right, so we can actually make the diazonium and isolate it, and then we can do a ton of different things from here. Okay, some questions about that one first. Okay, so a lot of the reactions that we're going to see coming off of here are pretty much just replacing this with some sort of group of our choice on the aromatic ring. So, do I have room to spread out from here? Okay, yes. So we actually have 6 different reactions coming off of here. Like in the notes, I sort of spread them out differently. But all of them are pretty much the same idea. You bring in some sort of replacement like nucleophile, and then a lot of the time you'll need a transition metal catalyst to help it get onto the ring. So CuCl is going to replace this with chlorine. CuBr is going to replace it with bromine. CuCN, like a cyano group, it's going to replace it with cyano group. So all three of those use copper. Turns out copper does not work great for iodine, but you can actually use Ki to do iodine. You can also replace that with an OH group. And the reagents you need for that are water and copper oxide. Technically, the water is actually the only thing that you require for that, but the copper sort of helps to catalyze it. And then finally, we can actually replace this with a hydrogen. If we do this weird reduced form of phosphoric acid. Okay, so a bunch of stuff you can do from here. This kind of opens up a lot of groups that we didn't really have any good way to stick onto a ring directly. Like, we've never seen a way to put an OH onto an aromatic ring. But now we have a way if we can get nitrogen on there first, which we'll sort of cover how to do that in a second. And then we can convert that to the diazonium and then go a ton of places from there. Or we can get it off the ring entirely and just replace it with a hydrogen. Okay, so I guess one super useful part of diazonium is it's easy to replace with something else. But another super useful part so it's also a good electrophile. So that should look like so if we have a nucleophile come in and attack it, then it's going to go for the outer nitrogen and kick that onto the positive charged nitrogen. And we're going to end up with whatever nucleophile attached to the outer nitrogen. Now we have an N double bond N instead. So we can actually use this to stick bigger parts of the molecule together too. And in fact, it turns out that having two aromatic rings connected together by an N double bond N, depending on what exactly is on those aromatic rings, gives you a ton of different colors, just because of the way the HOMO-LUMO gap works out for the molecule. And so these were actually the very first synthetic dyes that were created, like on industrial scales in the 1800s. Like, there's a ton of different colors you can get from these diazo dyes, just depending on which two aromatic rings you stick together with a diazo group in the middle. So if you have, for example, and one thing we can use as a nucleophile is for example, a ring with some kind of electron donating group on it. We can have this come in, do the attack from one of its double bonds, kick that over, and temporarily we'll get this, which you can show all the resonance for with the nitrogen stabilizing it with its lone pairs through resonance and a couple other resonance forms. So this is actually, if you look at it from the right ring's point of view and treat this whole thing as an electrophile, this is actually just an EAS reaction where this thing is attacking something and adding it para to the electron donating group. And then at the end we have to re-aromatize. Which gets us to here. Okay. So this is one example of diazodi, anything with two aromatic rings on either side of an N double bond N. Okay. Questions about that? Okay, cool. So the last thing that we really need to cover to tie this whole category all together is how do we actually get an NH2 on the ring in this first place? And the answer is we know how to stick NO2 onto a ring. We can do that by nitration. So what we're going to do is take that and convert it to an NH2. And that's going to be a reduction. Turns out actually H2 and platinum on carbon works fine for this. And H2. Or if you have other parts in your molecule and you're worried this will mess them up, so like an alkene somewhere else in the chain or something like that, you can actually use some different reaction conditions, so like Fe and HCl, or tin and HCl will also reduce it down. If you know one, probably H2 is the most useful to know though. Okay. Questions about that? Yeah.
Why is the ring more nucleophilic than the lone pair and the NH2 in the above reaction? Because I would just think that would attack and then that could be determinated, and then pair C would be broken up.
Right. If I had to guess, I would say probably because if the nitrogen itself attacked, you'd end up with 3 nitrogens linked together, and I think just the bond energy for that is not as favorable as the CN bond. Yeah. Okay, other questions about that? Okay, cool. So that's actually the end of this section, and I think that's a good place to wrap up for today. So I'll cut it off there.